Okay, so last time we ended the lecture with a quick either introduction or review of complex numbers. And so remember, complex numbers are typically modeled as a sum of two different quantities. One is a purely real number, which just means like an ordinary number on the real line. And then one is a purely imaginary number, which means a multiple of this imaginary unit I, which has the property that I squared is equal to -1. And so since these numbers have two components, right, they're determined by the choice of the real part, which is A, and the imaginary part, which is B, we can model them in the plane, right? So this is usually called the complex plane. And so in particular, once we fix a choice of A and we fix a choice of B, we can view the complex number as a point on this plane. And this lends itself to a natural notion of length of the complex number, which is just going to be calculated using the Pythagorean theorem. And so if z is equal to a plus ib, then the length is given by square root of a squared plus b squared. Sometimes this is called the modulus. And so, well, if you view your complex number as a point in this way, you can think of it as a vector. And this vector makes a certain angle theta with the real axis, right? And so this number theta is usually called the argument of z. And we saw that, well, if you write your complex number in this way, you can interpret it in polar form, where I can write z as r, which is the length of z, times e to the I theta, where I is again the imaginary unit and theta is the argument of z, right? So every complex number can be written in this form, meaning once you pick a particular length and once you fix a particular argument or angle theta, you can determine you determine a unique complex number. Right, and so this is very similar to polar coordinates. If you think back to multivariable calculus, this is kind of like polar coordinates, but for complex numbers. Right, and so what actually made this polar form work? Well, we have the famous Euler formula, which allows you to write the complex exponential. So if I plug in I theta, where theta is a real number, right? So it's just an ordinary number on the real axis. You can write e to the I theta as cosine theta plus I times sine theta. And so in particular, this gives you a connection between complex numbers and trig functions, which turns out to be a very powerful and useful connection. And so we're going to exploit this connection to make various calculations involving Fourier series and various theorems involving Fourier series easier to deal with. Okay, and so for the first part of the lecture today, I want to continue talking more about a few important properties of or results related to complex numbers, and then we're going to turn back to talking about Fourier series. And so the first thing I want to talk about are some consequences of the Euler formula. Which is just this formula up here. Great. So the first thing I want to talk about kind of makes the connection with trig functions a little bit more explicit. So these are sometimes called the de Moivre formulas. He's a French mathematician. I'm not very good at pronouncing French words. Right, and so these formulas are the following. Well, instead of just like writing down what the formulas are, let me just make some observations which will lead us to the formulas. So notice from Euler's formula, right, I have e to the I theta, I can write as cosine theta plus I sine theta. Right, so let me just copy this over. Well, let's see what happens if I look at now e to the negative I theta. The reason I'm doing this is because we know that cosine is an even function and sine is an odd function. So we're going to get some identity which is related to the first identity if I plug in minus theta, right? And so in particular, this is cosine minus theta plus I sine minus theta. Again, cosine is even and sine is odd, so this is equal to cosine theta minus, the minus sign will come out of the sine, minus I sine theta. But notice that in the first line, I have cosine plus I sine. In the second line, I have cosine minus I sine. And so if I add these two things together, the sine terms will cancel out, right? And so therefore, well, if I look at e to the I theta plus e to the minus I theta, this is just equal to 2 times cosine of theta, right? Because the negative I sine term here and the positive I sine will cancel out. And so this tells me then, well, if I divide by 2, if I look at e to the I theta plus e to the minus I theta over 2, this gives me cosine of theta, right? On the other hand, let's say I instead subtracted instead of adding. Well, if I subtract, well, I have positive cosine and positive cosine. So if I subtract the first line from the second, the cosine terms will vanish, and I'll be left with certain sine terms, right? So if I look at e to the I theta now minus e to the minus I theta, well, I'm going to have cosine theta plus I sine theta minus cosine theta, cosine terms vanish, and then minus negative I sine theta. And so the negative signs will cancel and you'll get positive 2I sine theta. So again, I've just subtracted these two lines, like one from the other, right? And so therefore, well, if I divide now by, instead of dividing by 2, I'm going to divide by 2I. You end up with e to the I theta minus e to the minus I theta over 2I is equal to sine theta, right? And so these two identities, which give you a particular way to represent cosine and sine as complex exponentials, are called the de Moivre formulas. And so typically, if you're working with some kind of trig identity that you're trying to prove, it sometimes helps to convert your trig functions into complex exponentials, because exponentials are a little bit easier to work with than trig functions typically are. Right, and so we'll do an example of this. So let's do like an application. And so what we're going to do is prove one of these trig identities that you've probably used a million times, but probably don't remember how to prove, because the kind of more elementary proofs are very complicated, clever geometric arguments. Right, so this example isn't going to use the de Moivre formulas exactly. It's going to actually just use Euler's formula. But we'll come back and we'll use these de Moivre formulas when we're talking about Fourier series, right? So I just want to look at an application of this formula. You can view, you can view the formulas we just looked at as one application. So now let's look at another application, right? So this is, say, the first consequence. Maybe the second consequence, instead of calling it an example, let me call this like proving trig identities, or let's say easy proofs of trig identities. Right. And so what we're going to do is, well, let's look at what happens. Right, so if you remember back from a variety of classes, you have all these identities involving like the sine of a sum of two different angles, right? And so there's some formula that says sine of a plus b is equal to some combination of sines and cosines. This is usually called some kind of double angle formula, right? And so what we're going to do is prove what is typically called the double angle formula in a very easy manner, just using complex exponentials and some basic algebra without having to do any fancy or trig calculations. And so the idea is, well, if I want to understand sine of a plus b or cosine of a plus b, remember that I can model these things together using a complex exponential. And so you're kind of naturally led to looking at, well, now theta will be a plus b, and you're led to naturally look at e to the I theta, where theta is a plus b. Right, so let's look at e to the I a plus b, right? And so this is by Euler's formula, this is cosine of a plus b plus I sine a plus b. On the other hand, well, since this is an exponential, remember the rules for exponentials say that I can write e to the I a plus b. Well, this is e to the I a plus ib, and I can write this as e to the I a times e to the ib. Well, why are we doing this? Well, I can now use Euler's formula again for each term separately, and I've separated the a and b in cosines and sines, right? So if I use Euler's formula again, this is equal to cosine of a plus I sine of a, and then all times cosine of b plus I sine of b, right? And so now let me distribute everything. If I multiply this through, I'm going to get cosine of a times cosine of b plus I times cosine of a sine of b plus I times sine of a cosine of b, and then minus, because I squared, remember I squared is -1, so when I multiply I times I, I'll just pick up a -1, sine a times sine b, right? And so what I'm going to do is collect the real numbers and the imaginary numbers separately. So this is equal to cosine of a cosine of b minus sine a sine b, and then plus I times cosine of a sine b plus sine a cosine of b, right? Well, this is all equal to e to the I times a plus b, right? I just evaluated it in a different way. And so we've shown that that in fact cosine of a plus b plus I sine of a plus b is equal to this term, right? Right, so this is equal to e to the I a plus b. And so therefore, cosine of a plus b plus I times sine of a plus b, which is equal to the exponential on the left, is equal to this, right? And so in particular, right, so this is like a fact, right? So if a plus ib, let's say you have, let me use different letters. Let's say you have two complex numbers, say s plus it is equal to x plus iy, right? Two complex numbers. This can only happen if x is equal to s and y is equal to t, right? And so this just boils down to the fact that, right, if I draw my complex number in the plane and the two coordinates agree, right, the real part and the imaginary part, or sorry, if the complex numbers are equal, then they're going to give me the same point in the complex plane. And so therefore the a and b have to agree, right? The real and imaginary parts have to be the same, right? And so if you show that two different quantities involving complex numbers are equal, the real part always has to agree with the real part on the left and right, and the imaginary part on the left has to always agree with the imaginary part on the right. And so if we look at this, well, what is the real part of the left? I have cosine of a plus b. On the right side, I have cosine of a, cosine of b minus sine a sine b. And so this tells me that cosine of a plus b has to equal cosine of a, cosine of b minus sine a sine b, right? So this is from the comparing the real parts. On the other hand, if I compare the imaginary parts, well, on the left-hand side, I have sine a plus b, and on the right-hand side, I have this other term. And so if I compare these terms, they have to be equal. So this tells me that sine of a plus b has to equal cosine of a sine b plus sine a cosine of b. Right, so this is from comparing the imaginary part. Right, and so this is a proof of what are called the double angle formulas, which are the two identities that we just derived. And the proof is really kind of harmless. You just have to do a bunch of algebra. It takes a little bit of work to sort out the algebra, but otherwise it's not very complicated. And the reason is that, I mean, this Euler formula is a very powerful tool, which, again, will simplify a lot of these calculations. Right, and so there are a variety of other trig identities which you've probably encountered at one point or another, and the proofs of a lot of these identities can be simplified as soon as you know Euler's formula. So this is the point of this example. Okay, and so now I want to, I think that's some two illustrative examples of why Euler's formula is important. So now I want to return to actually working with Fourier series, and we're going to talk about now complex Fourier series, which are typically, I mean, most people, once you leave this class, most people will just use complex Fourier series and they won't distinguish between sine and cosine because everything becomes easier. Right, so what's the idea here? Well, recall we have a full Fourier series is of the form, let's say I have some function phi of x, which is maybe 1/2 a0 plus some sum from n equals 1 to infinity of the sine and cosine Fourier series terms. So maybe an times cosine, let's say we're on minus pi to pi, right? So in this case, we're going to set L equals pi. Well, remember the formula for the argument of the cosine and sines was n pi over L. So if L is equal to pi, then those just cancel, right? So I have nx. Right, so the Fourier series in this case will become an cosine nx plus bn sine nx. Right. And so what I'm going to do is I'm going to go back here, remember these de Moivre formulas that we have. Well, remember if I have a cosine, I can write it as a sum of complex exponentials times 1/2. And anywhere I have a sine, I can write it as a difference of complex exponentials times 1 over 2i. And so I'm going to plug in these formulas to the full Fourier series, right? And so I can write phi of x. Well, I have this a0 term, nothing's going to happen here. But now in this infinite sum, I'll have an, well, if I use the first formula we derived above, this is e to the inx plus e to the minus inx divided by 2. And then I have bn times e to the inx minus e to the minus inx over 2i, right? And so we'll notice that now I've written my Fourier series as some sum of complex exponentials times some different, possibly different coefficients. But notice that for these terms, I have negative integers now, right? And here I have negative integers, right? So at the expense of allowing negative integers, I'm allowed to replace my cosine and sines with complex exponentials, right? And so let me now rearrange the sum. Maybe it'll make it a little bit clearer. So I can write this as 1/2 a0 plus the sum from n equals 1 to infinity. Well, let me collect like terms. So I have 1/2 an plus 1 over 2i bn times e to the inx, right? Just collect all the terms that I'm multiplying by e to the inx. And now let's do the same for e to the minus inx, right? So now I have an 1/2 an minus 1 over 2i bn times e to the minus inx, right? And so I have a certain term corresponding to e to the inx with a possibly different coefficient, and another term corresponding to e to the minus inx. And so what I'm going to do is, let's call this thing Cn. Let's call this coefficient C0, and let's call this coefficient C minus n, right? And so if I use this notation, well, I can write my function phi as the sum. Now n is not ranging from 1 to infinity because I also have negative integers, right? So negative integers are allowed. appear. Right, so now this is a sum from minus infinity to infinity of Cn times e to the inx. Right? And so what I've done is I've written my original full Fourier series as what's called a complex Fourier series using the de Moivre identities. Right? And so, right, so you may not have encountered this notation, sum from n equals minus infinity to infinity. So what does this mean? This means like you're looking at n can be 0, 1, 2, 3, 4, etc., up to some number n. It can also be minus 1, minus 2, etc., up to minus n. And you're taking the limit of these terms as n goes to infinity. Right, so I have some list, and right, so let's say I look at sum from n equals right, so the sum from n equals minus infinity to infinity of some sequence of numbers an is defined to be the limit as n goes to infinity of sum from little n is equal to minus n to big N of these numbers. And so this can be written as like a minus n plus a minus n plus, n minus 1 plus a minus n minus 2, and so on. Sorry, I had an issue with the pencil. an minus n minus 2, right up to a minus 2 plus a minus 1. So these are all the negative integer terms, which are new in this notation if you haven't seen it before. And then you add on like what the usual terms for the sum side, a0 plus a1 plus a2, and so on up to an, right? So this sum here, if I'm summing from some minus negative index to a positive index, this just means this sort of sum, right? So you're just kind of shifting the indices to allow negative integers also. And so this infinite sum from n equals minus infinity to infinity is defined as the limit as I let capital N grow larger of this quantity. So that was just a little aside if you haven't seen this notation before. Right. But the key point, though, is that if I begin with my full Fourier series and I apply the de Moivre formulas, I can rewrite my Fourier series using complex exponentials. And as we saw in an earlier example today, complex numbers make working with trig functions a lot easier. Okay, so this is why we're doing this. All right. Okay, so now I want to talk about the more general definition. Right, so if phi of x is equal to now sum from n equals minus infinity to positive infinity of some Cn times, well, remember in this example, to motivate what we're doing, we looked at the case where x is between minus pi and pi. So now let's look at a more general interval, right? So now we're considering the case where x is between minus L and L, right? So this is the domain for phi. And in this case, the complex exponential looks like e to the in pi over L times x, right? Just because the n pi over L is what shows up in the cosine and sine terms, right? Right. So if this is the case, well, we say that phi has a complex Fourier series. And so using the argument that we just ran through above, well, any function that has a full Fourier series in the sense defined in previous lectures also has a complex Fourier series if you want to allow complex coefficients. Right? And so note that the coefficients, which are called the Fourier coefficients, Cn, could be complex numbers. Right? But you can always kind of reduce to the previous scenario by using the de Moivre formulas in reverse to write this in terms of sines and cosines, right? Right, and so these coefficients are usually called the Fourier coefficients. And in particular, the nth Fourier coefficient, Cn, where n is now allowed to be negative or positive integer. Right? Okay, and so assuming your function has this representation, well, how do you calculate the coefficients? It turns out that we're going to be able to calculate the coefficients using formulas very similar to what we did in the sine and cosine cases. So let me write this as a theorem, which I'll break up into two parts. The first part is, remember that in order to calculate these coefficients, we needed some notion of orthogonality between the different sine and cosine terms. In this case, we need some kind of orthogonality or notion of perpendicularity between the exponential terms for different n. And so the first part of this theorem is exactly that. So if I look at the integral from minus L to L of e to the in pi x over L, and I integrate that against one of the other complex exponentials, it's going to turn out to be 0. However, because of some various technicalities related to working with complex numbers, we want to take the negative. So I'm going to multiply it by e to the minus im pi over L times x dx. This is sometimes called the complex conjugate. Right, so note the minus sign. Right, so this is sometimes called complex conjugate of the exponential. Right, so if I look at this integral, I have an orthogonality property, meaning it's equal to 2L if m is equal to n and 0 otherwise. Right, so this is the first property. And so this will allow you, excuse me, following arguments very similar to what we did with the sine and cosine Fourier series. Once you have this notion of the orthogonality, you can find a formula for the coefficients. And so the second part of the theorem is that for each n, I can write Cn as 1 over 2L integral from minus L to L of phi of x times e to the, again, notice where it's going to be minus e to the minus in pi over Lx dx, right? And so again, notice that there's a minus sign here, right? If you forget the minus sign, you'll be calculating the coefficient for minus n instead of n, right? So it's helpful, it's important to remember this, right? Right, and so this is bullet point 2 is assuming that my function phi of x is equal to its Fourier series. Right, but more generally, even if we don't know the function is equal to its Fourier series, we can still calculate this integral and calculate Cn. So this is, again, usually called the nth Fourier coefficient, regardless of whether or not we actually know that the function phi is equal to its Fourier series. You can still calculate these things, right? Because it's just an integral over a finite domain. Right, and so I think I'm going to leave out the proof because it's very similar to what we did in the case of sines and cosines. In fact, it's easier. If you want to see the calculations done, I would suggest actually just pausing the lecture and trying to do it yourself, and you'll agree with me, hopefully, using some of what we learned in the case of sines and cosines, that this is actually just an easy consequence of methods we've already developed. Right, you want to first prove the orthogonality, which is just a calculation involving taking antiderivative of an exponential, which is easy. And then for the second part, well, what do? You have this series here. We're going to plug this in for phi, right? You plug in this infinite series for phi. And since each term in the series involves a complex, or sorry, this shouldn't be negative. This should be positive, as written before. Right, so since each term in this series involves a complex exponential, and you're multiplying by another complex exponential here, because of the orthogonality property, every single term is going to be 0 except 1 when the integers agree. And so you're going to be able to use this to calculate the coefficient and prove this formula, right? So it's the same argument we've seen a few times before, right? Okay, and so, right, so that's what a complex Fourier series is. Right, so maybe as a quick example, let's suppose phi of x is equal to x. We've seen this example before, but we only did the sine and cosine coefficients. Let's say phi of x is equal to x on the domain minus pi to pi. And let's calculate the Fourier coefficients, the complex, right? And so, well, what are these equal to? Well, remember, we can, even if we don't know if phi is equal to its Fourier series, we can still calculate the coefficients. So that's what we're going to do here. And so in this case, L is equal to pi, right? We're just going to use this formula. So Cn is 1 over 2 pi integral minus pi to pi x times e to the minus inx dx. And so we're just going to integrate by parts as we did before. Right, and so right, so this is going to be my my u, this will be my dv, and so v is the antiderivative, so v is going to be minus 1 over in e to the minus inx. Right, you can take antiderivatives of complex exponentials just the same way you would for regular exponentials. It's the same formulas. And so if I use integration by parts, well, what I'm going to do is just move the 2 pi over so the formulas on the right don't get too cluttered. And so this tells me then that 2 pi Cn is going to be equal to, now let me evaluate this integral using integration by parts. So I have u times v, which is minus 1 over in x e to the minus inx, evaluated between minus pi and pi. And then I have minus the integral of u prime, or du, which is 1 times v. Right, and we're integrating between minus pi and pi. And so, well, the minus signs will cancel, and then I can factor out this constant term, right? So this just becomes plus 1 over in, right? But here, well, I can write this as, this is like a 1. Well, 1 is equal to e to the I0x, right? Because e to the 0 is 1. So this is actually a special case of our orthogonality result, right? And so e to the I mean, if we go back to bullet point 1, this is true for n equals 0 too, right? So this means that this integral is just going to vanish. Similarly, you can just calculate the integral and see that it's 0. So this is actually just 0. And so all we're left with is the boundary terms from integrating by parts. So we get 2 pi Cn is equal to, well, I have minus 1 over in times pi e to the minus in pi, and then minus negative pi e to the in pi, right? Plugging in x equals minus pi in the second part. And so this is equal to minus 1 over in. Let me factor out the pi, right? I have a pi in front of both terms, and then I have e to the minus in pi plus e to the in pi. Right, and then I can, if you wanted to, you could use the Moivre formula to combine this further. Right, in particular, I have Cn, well, now let me divide by the 2 pi, is equal to minus 1 over 2in. And then I have, well, remember, e to the I n theta plus e to the minus I n theta is going to be equal to 2 times cosine of n theta, right? And so this is equal to minus 1 over 2in times 2 cosine of n pi, right? So the 2's will cancel, and so I end up with cosine of n pi minus sine divided by in, right? So that's my Fourier coefficient. You can simplify this further since cosine of n pi will be either plus or minus 1, but let's not do that now. Right, and so the key point here is that I only have to do one calculation, right? Whereas before with sine and cosine Fourier series, we had to do 2 separate calculations to do the sine coefficients and the cosine coefficients. So this does simplify things a little bit. Okay, and so now, right, this is an introduction to complex Fourier series. Now we're going to turn to kind of the big question, which has been mentioned several times over the past few weeks, which is like, how do I know that my function is actually equal to its Fourier series? So that's the first part. And the second part is, how do I understand when this series will converge and when it won't, right? So up until now, we've been spending a lot of time talking about Fourier series. We still don't have any answer to either of these questions. And so this is what we're turning to now. And so now we're going to be talking about the convergence of Fourier series. And so more precisely, we're going to be looking at the question, when do we have, like say, some function phi of x in some sense equal to an infinite sum, right? So say sum from n equals minus infinity to infinity of Cn e to the minus I n pi over Lx. And so if you think about this question, it turns out that this is kind of a deeper question than may initially appear based on depending on how you've thought about convergence problems in math before. And so the idea is, well, there's 2 questions you can ask here, like in what sense do we mean that it's equal? Right, so do we mean that for every point that these things are equal? Or do we mean that, right, so maybe my function phi is equal to this infinite sum in some kind of limiting sense, and then if it's equal in some kind of limiting sense, how do we define the limit? And similarly, right, so basically an equivalent question is, well, how do we define or understand the convergence of this infinite series, right? So this is defined as a limit of some sequence of functions, some sequence of sums, partial sums of functions. Right, and so the question is, well, we need to understand this limiting process more precisely first to understand how or when this infinite series can converge. And then we can address a question of, well, what do we mean by phi being equal to this limit and in what sense and so on. And so in order to address this question more precisely, we first have to kind of take a step back and talk about convergence of series of functions. Right, so we're now not just going to talk about Fourier series, but more generally where I have maybe some function, say, call this fn of x. And so what does it mean if you're given a sequence of functions depending on the integers, say fn for each integer n, you have a different function, and you look at a sum like this, what does it mean for this series to converge, right? And so we're going to talk about this a little bit and then use what we've learned to return to analyzing Fourier series afterwards. And so it turns out that there's 3 important notions of convergence, right? So we're going to look at something like sum from n equals 1 to capital N fn of x. or maybe sum from n equals minus capital N to capital N fn of x. And we're going to study converging as n goes to infinity to some function f of x, right? And so it's going to turn out that there are three important notions of convergence, which we'll be working with. I mean, there's more than three important notions of convergence, but for this class, there's three that we'll be working with. Right, and so I'm going to go over all of these now. And so the first is probably the most familiar to you, which is what you would have learned when you first talked about infinite series of functions, for example, Taylor series. And so this is what's usually called pointwise convergence. Right? And so this means that this series will converge in the traditional sense, like as a sequence of numbers, it will converge, the infinite series will converge for each point x. That's why it's called pointwise. So we say that the infinite sum, or sorry, not the infinite sum, this sequence of partial sums, fn of x, converges to some function f of x pointwise if the following happens. So if I look at the difference f of x minus this infinite sum, and I take the absolute value, if this difference goes to 0 as n goes to infinity for each point x, right? So this means if I fix a particular point, look at this difference for each capital N, and then take the limit as n goes to infinity, the limit is 0, right? And so in this case, we say that f of x equals the sum from n equals 1 to infinity, fn of x pointwise. Right, so the idea is this infinite sum, which is always defined as a limit, right? It doesn't make sense to add infinitely many things unless you talk about it in a limiting sense, that this limit converges for each particular x as capital N goes to infinity, right? As capital N goes to infinity, it converges in the sense that the difference between f and this finite sum goes to 0, right? Which is a natural notion of this sum approximating f, right? And we want this to hold for each point, right? So you fix a point and you have this. So the key point is that, well, the rate of convergence may depend on x, right? Right, so the rate of convergence could depend on the point. Right, there could be some points where the convergence is faster than other points. Right, and so this may seem like an odd point for me to make right now, but we'll see in a minute when I introduce a different notion of convergence that this doesn't always happen. Right, and so this is also true if instead I could also replace sum from n equals 1 to n of fn by sum from n equals minus n to n of fn. It's the same definition, right? And so this is true for all of the definitions that we'll be working with below. So sort of following the book, I'm just gonna write sum from n equals 1 to capital N or n equals 1 to infinity. All the definitions carry over to sums like this, which show up when we're working with Fourier series. It just maybe simplifies the notation a little bit to use these kinds of sums, right? But again, all the definitions will transfer over to this, right? And so just as an aside, more generally, let's say we have a sequence of functions, say gn of x, not necessarily a partial sums, but just arbitrary functions. Well, we say that gn of x converges to f of x pointwise if I look at f of x minus gn of x. In fact, to be consistent, let me use capital N as my indice. So g capital N. Right, we say this sequence of functions converges to f pointwise if I look at the difference of f and g, that this converges to 0 as n goes to infinity. Okay. So I'm just using the same definition from up here, but I'm looking at the case, I'm replacing the special case where I have an infinite series by some other function g, and it's the same definition. Right. Okay, and so this is the notion of pointwise convergence. So the next notion of convergence is a stronger notion of convergence, which is called uniform convergence. Right, and so in this case, we have to fix a finite domain. So let's say fixed domain, say A to B, some finite closed interval. Right, and so we say that this sum from n equals 1 to capital N of our sequence of functions fn of x converges uniformly to f of x on this domain if the following occurs. Well, here we're going to no longer allow the rate to depend of converge. It's going to be very similar to this formula we have up here, right? Except uniform convergence is going to be when the rate of convergence does not depend on x. So you have the same rate of convergence for every point. So it's a stronger notion of convergence. And so the way to write this precisely is, well, you look at the difference between f of x minus the sum as before, right? But we look at the largest this can be on the interval. So we look at the maximum where x is between a and b, right? And so we require that this converges to 0, the whole maximum, as n goes to infinity, right? And so in particular, well, this is taking into account every point at once. Right, and so this requires that the rate of pointwise convergence is uniform over all x, right? So rate of convergence needs to be uniform over all x. Right, and so this is why it's called uniform convergence, right? Because it's not like this situation where, okay, each different x, maybe the speed that the series is converging is different. Here it needs to be uniform over all x. And so I realize that we're still doing things in kind of an abstract level. We'll look at several examples which will make this principle a little bit clearer after I define the three notions of convergence. Some of these examples may have to be left for the next lecture, depending on time, but we'll see. Right. So what's a good way to visualize this? So let's say, like, let me draw a sketch of a graph of my function. Let's say this is the graph of my function f of x. Maybe my function does something like this, right? And so what does this mean? Well, let's say this is my point A over here, and this is my point B. Let's look at this formula that we use to define this notion of convergence. So if I look at the maximum here, this means that the largest displacement between f and my series from n equals 1 to n of the fn's, the largest displacement has to decrease as n goes to infinity, right? So let's say I fix some very tiny number. Usually we use the Greek letter epsilon bigger than 0. Whenever mathematicians use epsilon, it's usually used to refer to some like arbitrarily tiny quantity, right, which you're going to like let approach 0 and like limit in the limiting case. And let's consider like a copy of the graph in like a small neighborhood, like so something like this, where the width of this is epsilon, right? So I kind of fatten the graph like this into like a tube, and so the width is like epsilon, which is this very tiny number, which we're going to think of as a converging to 0. Well, if I consider my partial sums, what does this mean? Let's say, I mean, it means that eventually if n is large enough, what does it mean that the maximum of this difference converges to 0? In particular, the maximum of the difference has to be smaller than this number epsilon, which I fixed. So you need max x between a and b of f of x minus this sequence of partial sums has to be less than epsilon once n is big enough, right? Since I'm letting n go to infinity, what does it mean that this quantity here converges to 0? What does it mean this converges to 0? It means that given any tiny number you want, eventually, if n is large enough, this whole quantity has to be smaller than that number, right? And so that's what I wrote out here. Epsilon is the tiny number. And so this means that the difference or the displacement between f and the sum has to be smaller than epsilon. So if this red tube that I drew over here has width epsilon, which is our small number, this means that the graph, which I'll draw in blue, of the sum has to stay inside here, right? So I don't know what it looks like, but it's going to be trapped between the red lines. And so then as I let n get larger and larger, the epsilon will shrink, right? I can let epsilon go to 0, and so eventually the graphs will match, and they have to do so uniformly, right? So this is like uniformly. Right, and so sometimes people refer to this kind of informally as like convergence of graphs, right? Because you have, it's not just like a notion of pointwise convergence, you need like the whole graph to eventually match up over the whole domain, like very, very closely. Right, and so similarly as before, you can define uniform convergence of more generally like a sequence of functions, where now you'll have, instead of the infinite sum, or sorry, the sum from n equals 1 to capital N, you'll have just some sequence of functions gn with the maximum out here. So I'm not going to write that out since we're mainly going to be looking at series. But actually, let me take that back. I should probably write it out because I'm going to do an example later using this notion. So more generally, like instead of just a sum of functions, let's just say we have some sequence gn. We say gn converges to f uniformly on a fixed domain, say a to b, if like the maximum of the displacement between f and g n converges to 0 as capital N goes to infinity. Right, so it's the same as before, but we're including this extra condition, which requires it to be uniform. Right. Okay, and so far we've talked about pointwise convergence, which is like the more familiar notion of convergence of series. And then we looked at a stronger condition, which requires that the rate of convergence is uniform over all of the points. So it's called uniform convergence. So the next notion of convergence is probably the least familiar because it involves integrals. And so this is something which in particular is commonly arises in statistics. And it turns out to be very important in Fourier analysis and mathematics more generally. So this is called mean square convergence, or sometimes L2. You'll see why the 2 in a second. Right, and so we say that the sum, our sum of functions, n equals 1 to capital N Fn of x, converges to f of x in the mean square or L2 sense, right? So this is capital L to the power 2. If, well, instead of looking at right up here, we looked at the difference pointwise between the function and the sequence. Here we're still going to look at the difference, say f of x minus the sum from n equals 1 to n of fn of x. But we're going to square it and we're going to integrate it over a domain. Right, so we'll say we integrate between a and b. And we'll say we want to look at the convergence on a fixed interval between a and b. So we want this limit, the limit of this integral, to go to 0. Right, so if I take the limit as n goes to infinity of the integral of the difference squared, that this is equal to 0. Right, and so it's going to turn out that of the, right, so here again, we look at the difference of the function and the sequence of partial sums. We square the difference and we integrate it. And we require that as you take the limit as n goes to infinity of this whole integral, that will converge to 0. Right, so it's kind of like an integral notion of convergence. So it's going to turn out that for working with Fourier series, this notion of convergence is actually the easiest to prove. And so that's the first thing that we're going to do after we go through some examples to understand the distinction between these three different notions a little bit better. The reason is because you have a power of 2 here, and it turns out that when you have like a power of 2, you can exploit orthogonality and things like that. And so we'll talk more about that in a few lectures, probably next lecture actually. Great. Okay, and so to end the lecture, I just want to indicate that I'll prove a proposition that indicates that the uniform convergence is stronger than the other two. And then in the next lecture, I'll begin with some examples which we can use to hopefully develop some intuition about these different notions of convergence. You always want to look at lots of examples. We're just running out of time for this particular lecture. Okay. Actually, let me take that back. It's probably better to end this lecture with a particular example, and then we'll do the kind of the theorem about these the next lecture. So I just want to finally, as we did with the other three notions, there's a more general notion of convergence. So if I integrate now the difference between f of x and some sequence of functions gn squared converges to 0 as n goes to infinity, we say that gn converges to f in the L2 or mean square sense. Right, just as before, I just want to indicate that you can, there's no reason why you have a sequence of partial sums here. You can replace it by just like an arbitrary sequence of functions and define the convergence in the same way. Right, so more generally, we've discussed three different ways for a sequence of functions to converge to our function f. Right. Okay, and so let's look at a quick example. And so this example is going to involve a sequence of functions rather than an infinite sum. So I'm going to look at the sequence of functions gn of x. It's a little bit easier to work with just like a sequence of functions rather than like a sequence of partial sums, because there's kind of less algebra you have to do to keep track of things. So it'll make this example a little bit easier. And so I'm going to define my function f of x just to be equal to 0 everywhere. Let's say we look at the particular domain between 0 and 1. And I'm going to define my function gn of x to be a piecewise defined function. So it's going to equal 1 if x is between 1 over n squared and 1 over n. So I'll graph this and the picture will become clearer, and 0 otherwise. Right, and so again, this is going to be on the domain 0 to 1. And so let's draw this graph. Well, this is my function f, right? So say this is 1 and this is 0. Right, so my function f is just equal to 0 for all points. Right, and so what is my function gn? Well, if x is between 1, let's say this is 1 over n squared, and say this is 1 over n, capital N. Well, if x is between these 2 points, my function gn is equal to 1. Right, and so otherwise gn is equal to 0. right? So Gn gives you, you get kind of this, it's like a step function, right? And so let's think about the three different notions of convergence for this sequence of functions, right? So first, let's think about pointwise convergence. Well, what does pointwise mean? Remember, let's go back to our definition from above. If we want to see if the sequence Gn converges to F pointwise, we just look at the difference between F and Gn, right? The more general definition over here. And we just want to see if the absolute value of the difference will converge to 0 for each x, right? Right, so let's look at the difference between, right, so what we want to do is fix a point x and look at f of x minus Gn of x, right? Well, f is just 0 for every single point. So this is just equal to absolute value of Gn of x, right? Gn is always positive, so this is just equal to Gn of x. And so the question is, does this converge to 0 as n goes to infinity for this particular x, or for each x, right? The rate doesn't have to be uniform, it just has to converge to 0 eventually for this particular fixed x. Well, let's imagine that I have my point x. Maybe my point x is right here, right? And so for this particular choice of n, if I draw it this way, Gn of x is equal to 1, right? So it's certainly not converging to 0. But notice that I'm allowed to let n go to infinity, right? I'm allowed to let these things go to infinity, n go to infinity here. And so as n goes to infinity, in particular, 1 over n gets smaller and smaller. And so eventually, if 1 over n is large enough, it's going to be to the left of x, because x is held fixed. And so once 1 over n is to the left of x, if n is large enough, then my function Gn is just going to be equal to 0, right? So note that if n is large enough, well, let's actually first, right, so sorry, the reason I paused is because let's first suppose x is not equal to 0, right? And so if n is large enough, then, and x is positive, then eventually x is going to be bigger than 1 over n, right? So for example, all we need is n is bigger than 1 over x, which of course can always happen. Like we can always find n bigger than 1 over x. And so after this point, right, as soon as 1 over n is smaller than x, or as soon as n is bigger than 1 over x, Gn of x is just equal to 0, right? And so of course the limit as n goes to infinity is 0, right? And so we've shown that as long as we fix a point x that's not 0, eventually, if n is large enough, my difference or the displacement here will be equal to 0. And so therefore, it does converge pointwise, at least if x is not equal to 0. On the other hand, well, if x is equal to 0, then by construction, notice that, well, 1 over n squared is always strictly bigger than 0, right? So Gn of x is equal, Gn of 0 is always equal to 0 for each n. And so we're okay here too, right? So Gn of 0 converges to 0 also, right? I mean, it trivially converges to 0 because it's equal to 0 at every point, right? And so what these 2 points show is that we indeed have pointwise convergence. So therefore, Gn of x converges to f of x pointwise on 0 to 1, right? Notice, however, that when we did this limit calculation, we required something that depended on x, right? So this depends on x, right? So in particular, as x is smaller, right? So if x is very small, so the rate of convergence increases. Right, and so if you come back to the picture here, right, so if it doesn't matter how big n is, there's still going to be some block of x where your function g is still very far away from 0. And so this would kind of indicate maybe that you're not going to have uniform convergence, right? So the idea is, well, we thought about this as kind of like convergence of graphs, where we drew like this little epsilon neighborhood around the graph of f. In this case, well, if I try to draw like some epsilon neighborhood, it's kind of like this little block here, where this is, say, height epsilon. It doesn't matter how big n is, though. There's always going to be some piece of gn that's very far from this neighborhood here. Right? N can be a million, a billion, a trillion, and so on. It's going to be very thin, but there's still going to be some part of positive length where gn is equal to 1. And in particular, this difference is very large, right? The difference between the graph of gn and the graph of f, or equivalently the displacement between gn and f in absolute value. And so this indicates that you're not going to have uniform convergence, right? Again, because you have this piece of the graph of g, which is always sticking far away from the graph of f, even though pointwise it eventually converges. And so let's do this more precisely. So we show that it indeed converged pointwise, but what about uniformly, right? Well, let's look at, again, the difference between f of x and gn of x. Now, in this case, we have to look at the maximum between 0 and 1 of this difference. And we need to see if this converges to 0 as n goes to infinity, right? Well, we know what the difference is equal to. It's just equal to the absolute value of gn of x, right? So this is equal to the max x between 0 and 1 of gn of x, right? But what is gn of x? For each n, gn of x is just equal to, right, you have some block like this. This is 1 over n squared. This is 1 over n. So the maximum is always equal to 1, right? Because I can always find some point y in between 1 over n squared and 1 over n, and gn of y is equal to 1. Of course, gn of y is always less than or equal to 1. And so the maximum is attained in this region, and it's equal to 1. And so, of course, 1 does not converge to 0 as n goes to infinity, right? Because if it's the function 1 is very far from 0. And so in this case, so gn does not converge uniformly to f, where my function f was equal to 0 on this domain. Right, so this is an example of a sequence that does converge pointwise for each x, but it does not converge uniformly. Right, so there are two ways to think about why the uniform convergence fails. The first is thinking about like what's going on with the graphs. No matter how big n is, there's still going to be a tiny piece of gn which is sticking out away from the graph of f. The graph of f is this blue line here. So no matter how infinitely large n is, there's still a gap. But there's always a gap between the graph of gn and the graph of f. On the other hand, if we think about this in terms of pointwise convergence, notice that the rate of the pointwise convergence depended on the point, right? And so if your rate of convergence depends on the point that you pick, it's not going to be uniform, right? Because the whole point of uniform convergence is that you can choose this condition to be independent of the point x. Right? Okay, and so in the next lecture, we'll look at another example where instead of like a gn, we have a sequence of partial sums or a series of functions, and we'll talk about uniform pointwise and mean square convergence for this example. And then we'll start talking more about the theory of applying this theory to the theory of Fourier series. So the first thing we're going to look at for Fourier series will be this notion of mean square convergence, which turns out to be the easiest to understand. Pointwise convergence and uniform convergence for Fourier series will turn out to be like a harder problem, although we'll still have some things to say about that. All right, thanks.